Hello everyone, welcome back to my channel. Today we're learning PyTorch, the deep learning framework that powers everything from ChatGPT to self-driving cars. If you want to build neural networks, train models, or working AI, you need to know PyTorch. It's one of the most in-demand skills in tech right now. So in this tutorial, we're going from basic to building completed neural networks. I will show you how tensor works, how to build and train neural networks, how automatic differential makes training possible. So I'm going to explain things the way I wish someone had explained them to me when I was learning, not just what each function does, but why you would use it and when. So I have created this Jupyter notebook with all the code. Link in the description. You can follow along or just watch first. Alright, let's jump in. So first, we're gonna install PyTorch and then check if you have GPU acceleration available. So first, you can in here, you check the PyTorch version and then check if your CUDA available. If it's available, it will also show your GPU information as well in here. So I'm using PyTorch version 2.5.1 and it shows my CUDA available is true. So if you see this part, then that means your code will run on the GPU, which is much faster for training. If this is false, that's okay. PyTorch works fine on CPU as well, just a little slower. So if you have a problem with your GPU setup, you can look at this part as well. All right, let's talk about tensors. So what is tensor? Think of like a NumPy array, but with superpowers. It can run on GPU for way faster computation. So the simplest way to create a tensor is just to pass in a Python list to tensor.torch. So let me show you. So here I have got a simple 1D one dimension tensor here. So just a list of numbers. Now I'm going to check it's a shape by doing this x dot shape, and then I'm going to check what's the data type. So and this is the output. We have a 1D tensor, list 1 to 5, and then the shape is torch dot size is 5. It does tell us I have a 5 elements, and the data type is torch dot integer 64. So it automatically figure out those are integers and made them 64 bytes integers. So now let's create something more interesting. A 2D tensor, which is basically a matrix. I passed a 3 by 3 matrix, and now let's see what it becomes. So it became a 2D tensor with 3 rows and 3 columns. So here's something interesting, like that caught me off guard when I first started. So when you convert a NumPy array to a PyTorch tensor, there are actually two different ways to do it. They behave very differently. So let me show you. First, I will create a NumPy array, just a Python list 1 to 5. Now watch. Now let's watch what happens when I convert it to different ways. Method 1, I'm using torch.tensor. Then I'm using torch.as_tensor, and then I'm going to print original NumPy, and then torch.tensor and torch.as_tensor. Um, then I'm going to modify. Oh, let's look at the output first. So this is the original NumPy array, 1 to 5, and then T1 we're using torch tensor, just a tensor, and then T2 they look same, T1, T2. So now let's modify the original NumPy array. So I just changed the first element to 999. Now let's see what happened to our tensor. So I'm going to just print out the tensor again. So this is the original, after change the numpy array to the first value to 999, we see the numpy array is this, and then T1 is still same, it unchanged. It's just a copy of the original numpy array. And let's look the T2. T2 is torch.as tensor. You see the first element already changed to 999. So it shares memory with the numpy array. That's because torch.tensor copies the data. It makes a completely separate copy. But torch.as tensor shares the memory. So it pointing to the same data in memory. So think if you are working with huge data set, like millions of images, making a copy doubles your memory usage. Using torch.as tensor can save you tons of memory. Just be careful though if you are planning to modify the original numpy array, because it will affect your tensor too. All right, let's move to specific data types. So PyTorch automatically figure out the data type for your tensors, but sometimes you want to specify a specific, like tell it which data type you want to be. So let me show you this. So in here we specific say we want to create a tensor with a flow 32, and then also this one we're going to show say torch.integer 32. So also we're going to print out it's a data type. So this is the results. So the first one, when we pass in the flow 32, it will come back with it. And then same thing for the second one. If we pass specific, we want an integer. So those are the common data types. So torch flow 32, this is where you will use 99% of the time for neural networks. It's a good balance between precision and speed. Torch flow 64, it's more precision, but it's slower and use more memory. So like only if you are doing like scientific computing. Torch integer 64, it's for integers, like when you are working with class labels in classification problem. So most of the time you are just using flow 32 for your neural network weights and data. It's just fast, works on GPU, and has enough precision for deep learning. Okay. Um, so PyTorch provides functions to create tensors filled with specific values. So you won't be always creating tensors from lists. A lot of time you need tensors filled with specific values. PyTorch have some really handy function for this. So first one, we're going to look at the zeros. So this create torch.zeros. This creates like a 3 by 4 tensor field entirely with zeros. Super useful for initializing things. This one, torch.ones, it will fill with ones. Same idea, but with ones. I will use this. I use this all the time when I need a mask or placeholder. Now here are the random ones, and pay attention because they look similar but do very different things. Torch.rand, it creates a random values, uniform distribution 0 to 1. So this gives you random numbers uniform distributed between 0 and a 1. And this one with n, torch.rand n, with this n gives you random numbers from a normal distribution. We're going to talk about why this n matters in just a second because it's actually really important. So this is the output. So this is one, torch.zeros and torch.ones. torch.random uniform distribution between 0 to 1. And then this is a torch.random n with normal distribution. Mean is 0, standard deviation is 1. Okay, so now we're going to talk about why torch_rand.n is very important. So let me show you the difference. So we got the torch.rand and torch.rand. They look almost the same. So just one letter different, but they are completely different. So let me create a 1000 random number here with each. So torch.rand and torch_rand_n, and I'm going to print print its mean and mean and max standard deviation. So here is the thing. Neural networks train way better when you initialize weights with a normal distribution. If you initialize all your weights to 0 or 1, your network later won't learn. So when you are building a neural network, you will do this. So this creates a weight matrix with 128 inputs and 64 outputs, initialized with small random values from a normal distribution. So you kind of use the rand n all the time. So sometimes you need to create a sequence of number. Like when you are creating index or plotting things, PyTorch has a function that works just like Python's range, but for tensors. So here we're going to say torch.arrange. So it will create, we say start with 0 and ends with 10 and take step as 2. So you will get value with 0, 2, 4, 6, 8. Also, you can create a evenly spaced value. So 9 space, it's a in here torch.9 space, we'll see create a 5 value from 0 to 1. So this is the tensor. So you have a 5 evenly distributed values. So 9 space is really handy when you want evenly spaced value. This creates so you just need pass like 2 endpoints and then how many values you want. So I use this all the time for plotting and visualization. Now we know how to create tensors. Let's actually do stuff with them. So operations are where things getting interesting. First, let me create two simple tensors and show you the basic operation. So this is 2a and b. Then let's try addition. So a plus b, it adds them element by element, 1 plus 4, 2 plus 5, 3 plus 6. So it will return 5, 7, 9. Then we're going to do the subtraction. It works same way like Python. So then now let's move to multiplication. So a times b. So it would be 1 plus 1 multiplied by 4, 2 times 5, 3 times 6. So this is the results. For division, it's same thing like how we do on the Python too. You can also do explanation in here. So it squares each element. So those things are super handy for computing things like mean square error. Broadcasting. So PyTorch is smart feature. Um, so you can do operations on tensors of different shapes, and PyTorch will automatically figure out what you mean. It's called broadcasting. Okay, now watch this. Let me add a single number to an entire tensor. So I create a tensor called A and then A plus 10. Let's see the results. So it will add 10 to each element. So PyTorch basically stretched that single number to match the tensor's shape. So here's where it gets really cool. Different shapes of tensor. So I created A with the shape 3 by 1, and then B just one row with 3 columns. So now let's watch what happens when I add them together, A plus B. So this is how it works. So if I create A plus B, it will basically it's a 1 plus this tensor, 2 plus tensor, 3 plus this tensor, and then it became this. So PyTorch stretched both tensors to make them compatible. It repeats that column cross and the row down. So this is super powerful that you will use it all the time in neural networks. Here's a quick tip that will save your memory. You know how most operations create a new tensor? Well, if you add any underscore to the end of the function name, it modifies the tensor in place instead. Let me show you the difference. So this is a regular operation. You create a new tensor called x, and then you create a new tensor called y, x dot adds 5. So let's see here. So x stays same. The y is a brand new tensor with the results 6, 7, 8. Now watch what happens with underscore. So same thing with x, and then we add x dot add underscore, and this comes like x stays same. X became 6, 7, 8. So the underscore tells PyTorch modify this tensor directly and don't make a new one. So in-place operations save memory because they don't create a copy. So if you're working with huge tensors like images or video, this can really add up. But be careful, once you modify it in place, the original value are gone, so you can't undo it. So I mostly use like in-place operations when I know I don't need the original value anymore. So you can also use this in-place underscore in other kind of operations like multiple in-place, subtraction in-place, divide in-place. Matrix operation. So now let's talk about the operations that really matter for neural networks, matrix operations. First up, the dot product. Remember this from linear algebra? You multiply corresponding elements and add them up. So this is A and B, two tensors. Then we do torch dot dot A and B. So what it does is one multiple 4, 2 multiple 5, and then plus 3 multiple 6. So which give us 32. That's the dot product results. So now here's the big one, a matrix multiplication. So we have two matrices, M1 and M2, and we specify the data type as a torch.flow. Then we do the matrix multiplication use this at operator. So M1 at M2, you can also use torch.mit, MUL. So the at symbol is a matrix multiplication. You can use this too, but the at is like cleaner. So each single layer in a neural network does matrix multiplication. So this is the fundamental operation you need to understand. So this shows like what happens when you use the matrix multiplication for two matrix here. So matrix 1 and matrix 2, and then when you do the M1 at M2, and this is what happening at the backend. Okay, let's move to the here. So this is probably the most important thing to understand about matrix multiplication. So you will run into shape errors, and this rule will save you every time. So look here. So n at n in here from two matrix, it must match. So when you multiply two matrices, their shape have to be compatible. So the inner dimension must be equal. So the first matrix second dimension must match the second matrix first dimension. So let me show you the actual code. So first we create two matrices, M1 and then M2. Then we multiple M1 and M2. So the inner dimension of both matrices are 4. So that's how it works. So the results of 3, 5, you just keep the outer dimensions. And here's another example. We have M3 and M4. So the inner dimension, one is a 4, one is 3, that doesn't match. So PyTorch will throw any error. So I probably spent hours debugging shape errors when I first started. So just remember the inner two numbers must match, and you get the out two as your results. So write it down if you need to. Now let's look at the aggregation operation. So it can reduce a tensor down to a summary statistic. Those are super useful for computing metrics and understanding your data. So first we create a tensor called X. It's a list of we pass a list of float. And then let me show you the common aggregation. So like x.sum adds all the elements up, 1 plus 2 plus 3 plus 4 plus 5. X.mean, so basically taking the average of the values. And then x max was the largest value, x.mean, smallest value. X standard deviation, STD is for the standard deviation. So the standard deviation always show you how spread out your data is. So you can also aggregate unknown specific dimensions. So this is really powerful for working with a batch of data. So we create a matrix tensor in here, and then you can do matrix dot sum up of all the elements, or you can pass like, oh, I want to sum up each column, so dimension equals 0. And then if you want to sum up each row, then you say dimension equal 1. So dimension 0 is a vertical direction, and dimension equal 1 is horizontal. So if a dimension 0, that's like 1 plus 4, 2 plus 5, and 3 plus 6. So you will get like 5, 7, 9. And then when you pass in the dimension equal 1, that's horizontal. So it will be 1 plus 2 plus 3, and then 4 plus 5 plus 6. You will get value 6 and 15. Okay, now let's talk about reshaping the tensors. So this might not seem exciting, but you would do this all the time in real neural networks. So neural networks are picky about input shapes. So your image needs to be reshaped, your text needs to be reshaped, everything needs to be exactly right shape. So let's learn how to do it. So first let's create a 1D tensor with 12 elements. So let's create from a range 1 to 11. So, oh, sorry, to 12. So it's start with 0 to 11. So then we reshape it to 3 by 4 matrix, and then reshape 2 by 6. Then you can also reshape to 4. -1 here is basically when you use -1, it means you want to let PyTorch figure out the dimensions. So I would say like you want 4 rows, and PyTorch figure out in its 3 columns to make 12 total elements, because our list have total 12 elements. So this is really handy when you're not sure of like one dimension tensor. Okay, so now how to flatten everything back to one dimension. So here's a function for it. So you can use the flatten. So for example, this is our original matrix. It's 2 by 3, and then after you flatten it, use the matrix.flatten function. It will flat to be 1D tensor. Also, you can transpose. So like swap rows and columns. You can use data T. So you will use transpose a lot when dealing with different matrix shapes for multiplication. Okay, so here, this is where PyTorch begins magical. We're talking about automatic differentiation, the thing that makes training neural networks possible without you having to write calculus by hand. So do you remember the like for calculus derivatives, chain rules? So PyTorch does all of that for you automatically. So you just need to tell it like um, track this tensor, and it will compute all the gradients you need for training. So it's honestly amazing. So let me show you how it works. So let's look some example. So first I create a tensor, and then I make sure I see requires the underscore grad it's true. So this tells PyTorch like, hey, I'm going to need the gradient of this later. So let's do some operations. So first I did like create a y, it's x plus 2. So x plus 2, 2 became 4 and 5. Then I'm saying I'm going to create a new tensor called z, y multiply 2. So that would be 4 and 5. And then you create a 32, 50, and then I'm going to calculate the mean. So PyTorch is remember every operation we do, building a computation graph behind the scene. So now I'm going to say out the backward. So and then I'm going to print the x dot gradient basically. So then let's see what we return. So PyTorch compute the derivatives for us. It figure out the derivative automatically. So the x gradient is a and 10 here. So that's same complex. Let me show you a super simple example here. So think about y equal x squared, x equal 3, and y equal 9. And then we compute the backward, the gradients. then x grand should be 6. So from calculus, we know the y equal x squared. It basically take the derivative is 2x. So x is 3, 2 times 3 is 6. So PyTorch got right. Now let's watch the gradient accumulation. So when I started, this part was a little challenge. So gradients in PyTorch accumulate by default. Let me show you what I mean here. So first we create a tensor x, and I tell it like I want please track all the gradients. So first let's do the backward. So as square dot sum, and then we did call the backward, and then it will calculate the gradients for x. So first time works right. Perfectly gradients is 2 and 4. Then we're going to second backward without cleaning any gradients of x. And now let's watch what happened. And the gradient doubled. So they went from 2 and 4 to 4, 8. That's because PyTorch add the new gradients to the old ones. It accumulate them. So to avoid that, this is the right way to do it. So first we need to clear the gradients first. We set x.grand.0 underscore. Then we call the y and then y.backward to calculate the gradients again. Then it will get x gradients is 2, 4. That looks correct. So you need to always remember call 0 underscore parentheses to clear the old gradients before computing new ones. So when you're training a neural network, you must call optimizer.0 grand parentheses before every backward pass. So if you forgot that, your gradients will keep accumulating from each batch, and your model will train completely wrong. So I made this mistake so many times when I was learning. So alright, this is where we're studying building actually neural networks. So PyTorch makes this way easier with the nn.Module. So let's start with building blocks of neural networks. A nn layer. This is also called a fully connected layer or dense layer. So you call nn.Linear. In feature 3 features and then output 2 features. So this creates a layer that makes 3 inputs and produce 2 outputs. Also, let's pick an insight. So we're going to look at the weight matrix shape and then the bias vectors. So the weight matrix is 2, 3, and this a bias vector with 2 elements. So PyTorch initialized those randomly for us. So let's pass some data through it. So we created the tensor x, and then we compute the output linear x. That's like w at x dot t plus b. So behind the scene, it's doing matrix multiplication and adding the bias. So w times x transpose and then plus b. B is the bias. So this is a fundamental operation of every neural network layer. Then we're going to talk about activation function. So linear layers by themselves can only learn linear relationships. That's boring. So to learn complex patterns, we need identification functions. Those add non-linearity to the networks. So let me show you the most common ones. So first I create a tensor X. Then I'm going to pass the ReLU, probably the most popular activation functions. So you can use the nn.ReLU. It just says like, this one says like, if it's negative, make it 0. Otherwise, keep it. It's super simple and super effective. So for the Sigmoid, squares everything between 0 and 1 used to be really popular. It's still kind of useful for binary classification. And this is the output. So like it make it turn the negative became 0, and everything else stay the same. And the same for the Sigmoid, they basically square the value from range 0 to 1. And then for the Tanh, it's similar, but the output is between -1 and 1. So sometimes it's better than Sigmoid. Now let's look the loss function, CrossEntropyLoss. So if you're doing classification like category, like cat versus dog, digital recognition, sentiment analysis, you will use CrossEntropyLoss pretty often. And here's the mistake like people make when they first started. I definitely did that too. So this is what I did. So don't do this. So the softmax give you probabilities, but the problem is like the CrossEntropyLoss already includes softmax internally, so you are playing softmax twice. So once in your model and once in the loss function. So your model will still train, but it will train poorly and slowly. So here is how you actually should do it. So you should use the nn.Sequential with nn here, and do not pass the nn.Softmax. So during the training, the CrossEntropyLoss handles the softmax, and then during the inference, you will apply softmax to get the probability here. Okay, now let's try a real one here on multi-layer neural networks. PyTorch's sequential container makes this super easy. So you can pass the input layer. I'm going to say 10 inputs with 64 neurons. And then I'm passing my activation function as n.ReLU. Then the hidden layer, I'm going to put a linear with 64 inputs and 32 neurons. And then activation again, and then output layer. 32 to 1. So we're basically stocking the layers like linear, activation, ReLU, linear, ReLU, linear. So that's the pattern basically. Linear layer, then activation, and then repeat. So the last layer doesn't have any activation because we will let the loss function handle it. So this network takes like 10 inputs, have 2 hidden layers with 64 neurons and then 32 neurons, and output a single value. So it's perfect for something like regression. So if you want to know how many parameters you're using, you're training, you can check by here. So total parameters, model.parameters, and then this results. So this counts every weight and bias in your model. So for a big network like RESNet 50, you will see millions of parameters. So in here we see 2,817 of them. Okay. So this we're gonna actually training a neural network now. We're going to build a model, feed it data, and watching it. So this is where it all comes together. So first, first step is generate training data. So first, we set up the random seed so we can every time we run, we will get same results. And then we're going to create the synthetic data so we know the exact relationship the model within. So I create a relationship where y equal this plus a little bit of noise to make it realistic, basically. So our goal is to see if the neural network can figure out those coefficients 2 and 3 on its own. So let me check the shape as well in here. So let's see the results. We have 1,000 sample, each with 2 features and 1,000 target values. Step 2 is move our data to GPU if you have a GPU. So this will make our training faster. So the 2x.2, the 2 device moves the tensor to GPU if you have one. So now let's split the data into training and test data. So we split this way. First 800 samples for training and last 200 for testing. So we never let the model see the test data during training. Step 3 is let's create the model. So first we're going to try a simple 2-layer network. So linear, we have 2 features and 16 neurons, and then our ReLU, and then our layer output layer again. So and then we do 2 device. So your model needs to be on the same device as your data. So now let's define our loss functions and optimizer. So two things before we can train. We need the loss function and an optimizer. So we are going to use the mean square error for loss function here, and then we're going to use Adam. Adaptive learning rate work well in this kind of thing. So Adam is the optimizer that will actually update the weights. And then we're going to set the learning rate is 0.01. So the learning rate is like how big of steps to take during training. Okay, now let's move to the actual training loop. So this is the habit of machine learning. Like, let me walk you through each step. So we're going to train for 100 epochs. That means we will see the entire training data set 100 times. And then for here, step 1, we're going to do a forward pass. We feed our training data through the model and then get predictions. And then we're going to calculate the loss, like calculate how wrong we are, the loss function compare our prediction to the actual answers. Then step 3, this is where the magic happens, zero gradient. So clears the old gradients, remember the gradients accumulation from earlier. So, and then we calculate we call the backward, compute all the new gradients automatically using autograd. Step 4 is update the weights. So the optimizer takes those gradients and adjusts the model's parameters to reduce the loss. And then we're going to save the loss and print it every 20 epochs. So we can watch the model improve. That's all the 4 steps, like forward, compute loss, backward, update, and repeat over and over until your model learns. Now let's evaluate the data, the model. So now let's see how well you actually learned. So we're going to test your own data it never seen before. So model.evaluate is set to evaluation mode. First, we set the model to evaluation mode. This turns off things like dropout that only happen during training. So this means like do not compute the gradients. And don't bother computing gradients. We're not in training basically. It saves memory and make it faster. Then let's see how we did on the test set. This is the moment of the truth. So let's compare a few predictions to the actual value. And if the model trained well, those should be really close. So let's take a look here. This is the actual. This is the predict. This is the actual, and this is the error. So they are pretty small and kind of close. Okay. Also, we plot it out to see how close they are. So it's kind of like pretty close for the prediction versus the actual value. So now we spend like all those times to training our model. You don't want to lose it, so we're gonna save it and then you can use it later. So save a model is pretty easy. You can just like call torch.save and then model.state dictionary, and then this is the way you want to store it. So the state.diction parentheses give you all the model's parameters, and torch.save save them to a file. And that .pth extension is the standard PyTorch convention. And then let's load it back. You can load later. So first you need to create the exactly same model architecture. So PyTorch only saves the weights, not the structure. Then you can load the weights with load state dict, move to your device, and set it to evaluate mode. So now you have got your trained model back. This is how you would deploy a model to production or share it with others. So one more thing before we wrap up, data loaders. So in the real world, your data sets are huge and you can fit millions of images through model all at once. So that's where data loaders come in. So let me show you how to using it. So let's create a data set. So you wrap your data in a tensor data set. So this is just pairs up your inputs and targets. Then you create a data loader. So batch size sets at 32, mean it will give you 32 samples at a time. And shuffle equal true. So randomize the order each epoch. This is important for good training. And here's how your training loop changes. So see, instead of processing all the data at once, we loop through batches. The data loader automatically divides your data into batches of 32 for you. So data loader give you three huge benefits, like more efficient GPU utilization. So GPU love parallel processing, and batches are perfect for that. Um, and also you only load one batch at a time, not the whole data set. So it can train data sets larger than the memory. Also, it's built-in shuffling and batch, so no manual work needed. This is how you will train models in the real world. Now you have learned the tensor, how to creating and manipulating data, neural networks like building models with nn.Module, training completed training loops, GPU acceleration, and safe loading models, data loaders for batch processing. Thank you for watching.